Hi, this video is to discuss the basic elementary signals. What are basic elementary signals? Basic elementary signals are used to analyze systems. We'll start with the first simplest one. The first signal will be called unit step signal. As a continuous time signal, in x-axis that's the time, and the vertical axis at t equals 0. So the unit step signal defined as equal 0 when t less than 0. Then you will see equal 0. And when t greater than or equal 0, it will be equal to 1. And it can continue till infinity. That's the unit step signal as a continuous time. As a discrete, u of n, how I represent it? It will be very similar to the continuous time signal, except it has discrete values at discrete times. So for any, that's not time, for any n integer, that's n equals 0, in minus 1, minus 2, minus 3, and so on, the value of the function is equal 0. So u of n is defined as 0 when n less than 0. But when n greater than or equal 0, it will be equal 1. This is 1, so you have 1 at t at n equals 0, at n equal 1, at n equal 2, 3, and so on till the end. That's the unit step signal. Let's go for another important one. It's called rectangular pulse signal. And it will be written like that. Rect t minus t naught divided by w. T naught is the time shift, and w is the width of the pulse itself. In general, in time domain, that's the time, and that's the y-axis at t equals 0. Since the rectangular function is shifted by t naught, so that will be the t naught, the axis of symmetry of the rectangle, far by t naught, and then you start to sketch a pulse symmetric about its own axis, and the width of this pulse is w. Example: plot the rectangular function t minus 3 over 2. So we know that the shift t naught is equal to 3, and the width of the pulse is equal to 2. That's the time, and that's the vertical axis at t equals 0. So we'll find t minus 3, it means t naught is equal to 3. 1, 2, 3, and we make the symmetric axis of the rectangular pulse. The width is equal to, and since it's symmetric, you will have 1 to the right and 1 to the left of the axis of the pulse itself. So that's equal to 2, and that's equal to 4. And as you see, the width from 2 to 4 is equal to 2. Great. How can we do that in discrete? Okay, in discrete, it's written like that. rectangle n minus n naught divided by 2n plus 1. So the axis will be n, and that's the vertical axis at n equals 0. Let's take, for example, that it's n naught is equal five. So we have 1, 2, 3, 4, 5, and that will be the axis of the symmetry of the this part. Well, 1, 2, 3, 4, 5. 2n plus 1, it's the width, the corresponding width of the discrete rectangular pulse. So let's say that you have here pulse. So you have 1, 2 to the right of the axis of the pulse, and you have another 2 to the left of the axis of the pulse. So the total will be 1, 2, 3, 4, 5. Let's write just the n, 3, 4, and that's 5, 6, 7. So that will be the width, which is equal to 2n plus 1. Why we write 2n plus 1? We have n to the right of the axis, which is 2, and n to the left, which is 2. So that's 2n plus 1, the one in the middle that it's drawn, plotted on the top of the axis of symmetry. So in this example, 2n plus 1 is equal to 5. It means n is equal to 2, as you see here, and the rest will be 0. Exactly similar to the continuous. It will be 0 everywhere to the right and the left of the pulse, just around. So that's the way you represent this discrete time signal for the rectangular pulse. Let's now move to the third type of the it's a signum signal, and that's the time axis, the vertical axis. So it's defined as sine t. It's equal to 1 when the time is greater than 0, and -1 when t less than 0, and 0 at t equals 0. You take the average, 1 and -1 divided by 2, so the value is 0 at this. That's simply express the sign. It means when the time is positive, it's equal 1. When the time is negative, is equal -1. When the time is 0, the value is equal to 0. Okay, how you do that in discrete time signal? That's n axis. The vertical axis at n equals 0. And you have 1, 2, 3, -1, -2, and so on. It's defined as sine n is equal to 1 when n greater than 0. So that's 1. And you continue. And it's equal to -1 when n less than 0. And you continue. And 0 when n equals 0. So that's the sine signal for discrete time signal. So now let's go to the fourth one. Unit ramp signal. And it's written like that, R of t. That's the time axis. That's the vertical axis at t equals 0. Is defined as R of t is equal 0 when t less than 0. And when t greater than or equal 0, it's equal t. T is a straight line, if when you think about it, of slope 1. So you just do it from t equals 0. When t is equal 0, is equal 0. When t equal 1 is equal 1, 2, 3, and just go till infinity. So the slope is equal 1. That's the unit ramp, because the slope is equal 1. What about discrete time signal? It will be very similar. That's n axis, vertical axis. So R of n is defined as 0 when n less than 0. And when n greater than or equal 0, it will be equal to n. So when n equals 0, it's equal 0. When n equal 1, it's equal 1. When n equal 2, it's equal 2. When n equal 3, it's equal 3, and so on. It will be very similar but discrete. Discrete at time. Of course, you can continue. Okay. So let's go to the fifth one, which is unit impulse signal. And it's written like that. And you read it delta of t. Delta of t is defined as it's equal to 0 when t not equal to 0. But when t equal to 0, it's equal to infinity. Huge. So if this is a time, and that's the vertical axis at t equals 0, it's 0 everywhere. Just appear in the middle. So let's choose different color. And we make it like that. A thick line with arrow like that. And write delta t. But just let's look for the practical one. How can we represent it? Actually, the impulse function, we can consider it as a very narrow signal around time equals 0. If this is the time axis, and that's the vertical axis, and let's just assume we have a very small rectangle and let's say that is equal to negative epsilon. It's a very small number, and positive epsilon, very small number, less than 1. You can say, for example, that epsilon is equal 0.01, for example. Very small, something just close to t equals 0. But we try, you imagine how can we get this impulse, unit impulse. And the height should be equal to a value that it make the area equal to 1. So the width of this rectangle is equal epsilon minus epsilon, which is equal to 2 epsilon. So to make the area equal to 1, the height will be equal 1 over 2 epsilon. This rectangle, you can find that the area is equal to 1 over 2e, the height, time the width, which is equal to epsilon, is equal to 1. But there is condition. Epsilon should be very, very small. So you can say that this pulse, xb of t, call it pulse, defined as it's equal to the amplitude 1 over 2 epsilon when epsilon greater than 0, less than 1. And it's also, you can say, where is the epsilon? That's for t greater than negative epsilon, less than positive epsilon. And epsilon is very small value. And 0 otherwise. This pulse, xp, you can get it to delta by doing something very simple. You will say that delta of t, when it will be equal to this pulse, when the epsilon is getting closer to 0, when this one gets very tight, then it will be the unit impulse. And why we call it unit impulse? Because the area is equal to 1, as we explained. So that's the definition of it. Actually, you can say that the integration of this pulse from negative epsilon to positive epsilon, any delta of t, delta t, it's always equal to 1, all right? But this is for epsilon, very small value, all right? And for the time between negative epsilon and a positive epsilon. But if t not equal 0, this is around 0, that will be equal to 0. So you can say that this is the definition of delta t after the mathematical explanation we just did. So that's very important integration. Let me just put it for here. From negative epsilon to positive epsilon, delta t is equal 1. All right, and epsilon is so small. All right. Actually, the unit impulse signal, it's also called delta or Dirac delta signal, has many important properties. We'll take it one by one. First, what happens if we are multiplying function by delta t? What is the result? Well, let's just imagine that we have a function here and we have a signal delta t at t equals 0. So if you multiply this delta t by the function, you will get the value here. What is the value here of this function? It's corresponding at t equals 0. So the value of this function is equal f of 0. And f of 0, you will write it equal to f of 0 delta t. So you multiply delta t by the function, so you'll get this value. So it's not anymore equal to unit impulse when you multiply the impulse function by the other function. So it will be equal if not delta t. What does it mean? It means the result will be equal to impulse, but not unit impulse. It's of magnitude f of 0 delta t. Example. Let's say that we have 4 over 7 plus t squared delta t. So what is the result? In this case, this will be considered as our function f of t. So I multiply it by delta t, so we'll find the value of this function at 0. F of 0, it means you put t equals 0 to this function, 4 over 7 plus 0 squared. It's equal 4 over 7. So the result will be equal to 4 over 7 delta t. It means you're going to have impulse function of amplitude 4 over 7. There is something interesting. What happens if you have delta t minus 3? What does it mean? It means that this pulse is defined at t equal 3, or the impulse or unit impulse, it's shifted from 0 by 3, 1, 2, 3, and then you have your unit impulse here. That's delta t minus 3. Well, let's do the same example. What happens if we have 4 over 7 plus t squared multiplied by delta t minus 3? Okay, in this case, that's our ft. So when you have f of t multiplied by delta t minus 3 will be equal the function at t equal 3 delta t minus 3. You will have impulse function or impulse signal and its height f of 3. In this example, f of 3 is equal, I substitute by t equal 3. So you have 4 over 7 plus 3 squared. That will be equal to 4 over 7 plus 9. 4 over 16, it's 1/4, 0.25. Then we can say 4 over 7 plus t squared delta t minus 3 is equal to 0.25 delta t minus 3. Great. Let's take the last thing. What happens if you integrate 4 over 7 plus t squared delta t, and you want to integrate from minus infinity to positive infinity, and the integration with respect to dt? Well, we know that the integration of delta t, it's equal to 1 if you integrate it from minus infinity to plus infinity. So if you do that, the result will be, if you consider this f of t, the result will be f0. It will be f of 0. All right. Let's just do example on that to explain how can we get it. Well, f of 0 we did before for this example is equal 4 over 7. So the integration from minus infinity to positive infinity, 4 over 7 plus t squared delta t, it's just equal 4 over 7. Because we know the integration of the unit impulse itself is equal 1. And then when you multiply it by the function, you are changing the amplitude of the impulse. It's not unit impulse anymore. So the area is not going to be 1 anymore. It's going to be the new value 4 over 7. Just the last example. What about 4 over 7 plus t squared times delta t minus 3 dt, and the integration from negative infinity to positive infinity? Well, it will be the function at t equal 3, which is equal 0.25 as it before. Okay, I think we're done with the basic elementary signal, and next video will be on the operation on the signal itself. Till we see you, have a good evening.